Hello everyone and welcome back to our monthly research seminar. It's good to have you with us. It's been a topsy-turvy last 10 days with goings on around the world, but it's great that you've taken time out to rejoin our research family. For any newbies in the audience, my name is Dave Lamb. I'm the Chief Scientist of Food Agility and I'll be the MC for our presenter and presentation today. I'd like to take the opportunity to acknowledge the traditional landowners or traditional owners of the many lands and waters on which we all live and work. I'd like to pay my respects to elders of all these lands and waters, both past, present and emerging. Now, for those of you that are unfamiliar with us and our program, we're a CRC dedicated to unlocking the power of digital to transform our agri-food sector. So before I move on to introduce our speaker, just a reminder on some of the housekeeping. The session is being recorded and ultimately we will make the recording available to you. We certainly welcome questions and please use the Q&A tab at the bottom of your screen, not the chat tab. I'll keep an eye on those off to the side, but the Q&A tab is the way your questions can come home. Whilst not possible for you to ask questions direct of the presenter, I'll work through those posted on the Q&A tab at the end and we'll have a conversation around them. Now to our seminar topic. A digital twin is a virtual model designed to accurately reflect a physical object. Or is it? Guidehouse Insights published an online discussion 3 years ago asserting that digital twins are actually overhyped. Now, I'm not suggesting that's the case at all. In fact, when you look at the report, the Gartner's 2018 hype cycle for emerging technologies places digital twins right at the peak of inflated expectations and estimates that digital twins are about 5 to 10 years away from the so-called plateau of productivity, that is, from being an operational technology. Well, so we think. But that is, of course, if we constrain our thinking to what a digital twin actually is perceived to be. In fact, digital twinning has been around for decades, but it's only now, thanks to computing power and some pretty clever analytical and visualization tools, that digital twins are really coming to life. And this is what today's presentation is about, where the art of the possible of digital twins becomes the science of the plausible. And so it's with great pleasure that I introduce to you today's speaker, Dr. Liqi Han from the Queensland Alliance for Agriculture and Food Innovation, or QAAFI as we know it, which is a research institute in the University of Queensland. Originally from a computer science background, Liqi has been working with plant scientists and horticulturalists for more than 16 years, using his IT skills to help explore plant signalling, carbon transport, light interception and distribution, as well as spray dynamics. At QAAFI, Liqi has led the development of a high-performance ray tracer and an orchard simulator to improve horticultural designs towards better light quality for better yield. So are we talking about digital twins of real environments or the opportunity to completely rebuild real environments around digital progenitors? And this is the excitement of today's presentation. Liqi has also been responsible for a project to innovate digital twin technologies powered by high performance computing and artificial intelligence to reduce horticultural spray drift for protection of the Great Barrier Reef. So it's a privilege to have you with us today, Liqi, and we look forward to hearing more about your DigiHort initiative, and in particular, digital twins for innovation of future horticultural systems. Welcome, Liqi.
Okay, thank you. Thank you, David. And hello, everybody. As David just introduced, originally I came from a computer science background, but I've been enjoying our agriculture and I've been enjoying working with agricultural researchers in the past 16 years. I hope you can give me some comments to improve this research. In this digital twin presentation, you will see some 3D computer simulations and graphics. I would like to explain a little bit that these simulations are different from computer games or the ordinary virtual reality applications. The essential difference is that our simulations are driven by physical laws or scientific models. The future orchard systems feature high-density, narrow canopies with fruiting walls, unconventional layout, with intensive pruning and trimming practices. But the development of such orchard systems are not only time-consuming and labor-intensive, but also face challenges in potential overuse of chemicals, in maintenance of fruit quality, and in response to climate change. At the national level, there have also been multiple strategical plans. On one hand, we want, for example, for horticulture, we want the horticulture industry to keep growing and even to double. On the other hand, we want to reduce emissions and agricultural pollutions. Personally, I believe a strategical pivot would be the digital agriculture to achieve higher precision, and then we can get better yield, lower cost, and less pollution. So the DigiHort research is part of this great digital agriculture or precision agriculture efforts. Our DigiHort solution is based on digital twins powered by high performance computing and artificial intelligence. In this case, we talk about artificial intelligence, not just about machine learning, but also about complex system modeling. So the DigiHort includes two components. One is light environment optimization to improve orchard designs, and the other is spray practice optimization to improve orchard management. So in this case, we define digital twin not only as a replica of a real world object, but it could also be the case that we have a digital twin at first, and then we can convert this digital twin into a physical twin. The general idea is to optimize in silico before acting in situ. For orchard designs, it will be good if the designs can be optimized before becoming reality. Because once the designs become reality, once they are planted in the real world, it could be too late or too expensive to change our mind. So with this digital twin tool, we can simulate different scenarios from density training to orchard layout or orientation, and even protective cropping. For example, this is the original design of 2 trellis training systems for jackfruit trees by my dev collaborator, Yan Desbalis. This includes 2 training systems. One is called the horizontal system, the other is called angle system. Yan suspects that the light quality of such narrow canopies could be very sensitive to rule orientations and latitudes. So based on Yan's designs, we have set up some digital twins of these scenarios, which can help evaluate the different systems with different orientations at different geolocations. When we talk about the light capture, it's not just about the light interception by the entire canopies, but also about the light distribution across the canopies, from leaf to leaf, from branch to branch, from tree to tree, from row to row across the orchard. Here, the spectrum from blue to red represent lower to high energies captured by individual leaves. And this curve represents the percentage of leaves with different energy levels. This allows us to evaluate light distribution in both an visual way and also a quantitative way. We can also calculate the sum of photon flux absorbed by the leaves, either by a single tree or by the entire orchard, for us to understand the overall capability of light capture. To investigate the impact of rule orientation, we can rotate this training system with different angles and see what happens to its middle rule light distribution. So now I'm going to rotate the orchard. When I'm rotating the orchard, you can observe what happens to the light distribution, as well as the overall light capture. Okay, let's do it again. Oops. Now I'm going to rotate orchard. So traditionally, the rows are north-south oriented. In this example, for this specific latitude at this specific time point, we can see the 75-degree. The 75-degree rotation might be the best in terms of light energy absorption. Of course, if there is a big mountain on the west or on the south of the orchard, or if the orchard is going to be placed on a big slope, we can also simulate those carrying effects. And we're also able to integrate the data from BOM to configure these simulations so that we're not only able to look at light distribution across the orchard and spatially, but also we can have a look at the light capture over the year. Another example is pruning. In practice, we can easily prune trees with machinery into square or cuboid shapes, and I hope this could help improve light quality and reduce vigor. But with computer simulations, we found that the machine trimming actually doesn't touch many of the low energy leaves that are located, at the inside or bottom parts of the canopy. In terms of energy absorption per leaf area or common productivity per leaf area, there's no obvious improvement after the trimming. Here we define a common productivity of a leaf as its photosynthesis rate times its leaf area. So in this case, we significantly reduce the number of leaves, but in fact, in the average light capture as well as the average common productivity is not changed obviously. So if we just remove the low energy leaves, which I call it leaf shearing, just remove those low energy leaves, the result would be quite different. It has similar number of leaves with the machine trimming. The number of leaves are similar, but in terms of energy absorption and also carbon productivity per leaf area, this leaf shearing is much better. In these simulations, we simulate explicit leaves with explicit rays traveling across the leaves involving light reflectance, transmittance, energy absorption. Such level of complexity could be a challenge. If you want more details with better accuracy, you could lose efficiency. If you want better efficiency, you often have to sacrifice the level of details. In this research, we want both accuracy and efficiency, not to balance them, but have both of them. The way is through high performance computing. As David just mentioned now, because of the power of computing, now the digital twins can really do something that is practical. So this is an example. The traditional programs, made with serial programming, can only use one CPU, no matter how many CPUs you have in your computer. So we have built a high-performance light simulator that can make full use of all CPUs as available. For example, in this case, my desktop computer has 64 CPU cores. The serial program can only use one of the 64 cores at any time point. At the same time, the other 63 cores are simply, doing nothing. With the parallel programming, we can make full use of all those 64 cores. As you can see, every core is 100% used in this case. And that's why we can achieve much better performance and a much higher speed of simulation without sacrifice accuracy or complexity. So with high performance computing, now we can finish a single virtual experiment in 26 minutes. Doing that with the serial program used to take more than 6 days. We have also developed the HPC, the high performance computing approaches that can run with the GPUs rather than CPUs. to make it affordable and adoptable for ordinary growers, researchers, and digital horticulture businesses. Well, that means, people don't have to worry about supercomputer. You don't have to worry about high performance computing cluster. You need to have a desktop computer with a commodity GPU card. Then you can run simulations with high performance. Okay, so the spray component, it's also about to optimize in silico before acting in situ. It's not only for future orchard systems, but also for existing orchards. Firstly, we need to create an orchard digital twin, and then implement spray simulations with orchard digital twin to find out the optimal setting of the sprayer, and then to instruct the spraying practices. The instructions can be used to guide traditional spraying practices with this ground sprayer, for example, or all these instructions can be loaded to robotic and automatic sprayers to guide unmanned practices. The benefit of doing this is that we only need an accurate geolocational input rather than putting sensing, computing, and controlling systems all on board. We just need that, simple input and then control the sprayer to do the precision spraying. So far we have developed a high performance spray simulator based on digital twins and powered by high performance computing and complex systems. With this simulator, we can simulate the movement of every single droplet from its origin to its destination. And the movement all the way is driven by physical laws or scientific models. We're able to support different spray movement models. And we have verified this technology through an experiment where the digital twin simulation in general matches their physical twins in the field. So this gives us the confidence to move forward to use this digital twin simulation to do some investigations. The technology allows implementation of computer simulations with different scenarios where the spraying facilities can be adjusted to optimize pesticide applications. For example, we can adjust nozzle type, including spray angle, type of corns. We can switch nozzle on and off. We can change the nozzle direction. We can change the spray pressure, tank capacity, sprayer, tractor speed, as well as the environmental factors such as the wind speed. And we're able to trace the explicit movement of every single droplet and in every millisecond from a nozzle to target. And by this, we can evaluate the amount of off and on target droplets to say, how much percent of the spray touched the canopy and how much percent missed the canopy. And we can also investigate the coverage of spray over canopy surfaces and evaluate the potential penetration across canopies. So in terms of ultra digital twins, this technology is compatible with the different 3D ultra digital twins, whether it is a scan from a LiDAR or it's a photogrammetry result. As long as it is 3D point cloud, we can work on it to simulate the spray practices. So this is an example of a sprayer that has been used by the Queensland Walkman Research Station. It has 15 nozzles located in 4 zones. The right table here lists the settings that can, the settings have been long used by the orchard workers. So we can use digital twins to help estimate if these settings are good or not. So they haven't changed these settings, for long. But let's see what how it performs. So this is the result. Only less than 30% of the spray touches the canopies, and more than 70% miss the canopies, which means it's not good. Initially, we thought the large tree gap, the large tree gaps in this case could be the major cause of the spray drift. But a digital twin experiment indicated that from each nozzle's point of view, the droplets simply fly into the air. Most of the droplets fly into the air above the canopies. So that part of the drift composed the major spray waste. Then we made some changes to sprayer settings, particularly to the spray angles and nozzle directions, and found that the off-target spray can be reduced by 36%. So in the case above, with the default settings, 71% of the spray wasted, becoming nothing for no gain. And just after we changed nozzle directions and angles, which means minimal cost to the growers, we can reduce that spray drift from 71% to 35%. Well, that means saving 36% cost and waste with no need to retrofit, with no need to replace the existing sprayers. Of course, if we equip this technology, if we equip automatic sprayers or robotic sprayers with this technology to allow the switch of the individual nozzles on and off real-timely at the right locations, that way the spray drift can be further reduced. So these brown bars are those spray crossing the tree gap. If you can turn off nozzles real-timely according to that gap, then we can save more spray from the practices. In addition to the hit and miss, we can also visualize the distribution of droplets on surface of the tree canopies to evaluate the coverages. So in this case, every single grade represents the color of each grade represents the number of droplets touching that part of the tree canopy. The colors from blue to red, again, represents the levels of droplets from lower to higher level. Just now, we look at the entire sprayer's hit and miss, as well as the performance of each individual nozzles. We can also look at groups of nozzles in different zones to say where the droplets end and how we can adjust the zones to improve the spray, to improve the efficacy, and to improve the on-target ratio. This is not only useful for the growers to adjust their existing machines, but this can also be used to help the sprayer manufacturers to improve their designs to suit the different orchard systems, especially the future orchard systems that are going to be widely planted in the next 10 years. We're also trying to see the impact of tractor speeds on spray hit and miss. Under the sprayer settings, the same sprayer settings, but with different tractor speed, from 5 kilometers per hour to 20 kilometers per hour, we can evaluate the hit and miss. So here we can see the hit and miss ratios are very similar, about 30% to 70%, but the total amount of applied pesticides are quite different. And the spray coverages are different too. The growers and horticultural researchers can decide which result is better depending on different planting systems, different pest types, the balance among the different factors such as pest control crop growth and yield, cost saving, as well as the pollution and emission reduction could be considered to decide which sprayer or what sprayer setting or what tractor speed could be the best for a particular planting system. So basically, we expect this to become a decision support tool to help the growers, to help horticultural researchers to make decisions. This is an example of spraying on a mango trellis system. We can say, some fruiting areas, for example, here and here, the fruiting areas are potentially oversprayed, which might affect those fruits' quality and market values. So with this from different angles, we can help the growers to adjust their sprayers to improve the heat ratio, to reduce the waste, and to try not to overspray some fruiting areas, for example. In future work, we are planning to allow the digital twins to detect fruit qualities such as sunburn and blush. This is mango tree, for example. The blush represents good quality and high market values, while the sunburn is damage to the fruit quality because overexposure to the sunshine, and it represents low market values. So with the digital twins, on one hand, we want to be able to infer the supply chain, how many high quality fruits we can provide, where are they, in which farm, in which row, on which tree, how soon would they be available. On the other hand, we can use this to find out the correlations between fruit and the light qualities. Because we can simulate the light ray traveling, not only across the canopies, across the orchard, but also over the year, and we can have the exact locations of those sunburn fruits and blush fruits, and we can try to find out the correlations between the light environment and the fruit quality, and this can be further used to support the innovation of future orchard systems. In the trellis system I demonstrated just now, it is very good in terms of light penetration, light distribution, but in practice, the horticultural researchers have found that that could lead to more sunburn fruits. So we can do, to just use this as a tool to help the researchers and the growers to evaluate different scenarios and to support their decision making. I would like to thank these great people, my leaders, colleagues, and students across UQ, DAF, and our industry partners for their great support and contribution to this research. And also my sincere thanks to Food Agility and Professor David Lam for giving me the opportunity to present the DigiHort technology. And thank you everyone for coming online. I look forward to your questions. Thank you.
Thank you, Liqi, and a visually stunning presentation as well, which demonstrates the power and the value of that computational mixed visualization of the digital twin. So have quite a few questions come in. So, and everyone, please keep the questions coming in. We've got a little bit of time. So in your earlier slides, you made a reference to leaf shearing as one of the options of canopy management, with the reasoning of, knock out the low energy leaves. In practice, is there a pathway, a mechanical pathway to achieving leaf shearing, bearing in mind that you're targeting those low energy leaves?
Well, I called it leaf shearing because I was inspired by the sheep, the wool shearing. So in practice, I haven't realized there are any current approaches to doing that for trimming the leaves precisely. But I just inspired by that, I tried to demonstrate, okay, this could be something that could be worth to be investigated in the future, so that people can do some, leaf shearing quickly, efficiently, and to improve the tree's overall performance.
You may not be far from it, from the truth, because if you flip the analogy you've given around sheep, for example, 2 weeks ago I met the owner of the tractorless vineyard, and in fact they use sheep to moving amongst the vines, not only to monitor or to manage the cover crop, the interrow, but also desuckering when there's green shoots low down in the vines. The sheep can nip them off, and also they do selectively pick out leaves from within the canopy. So maybe by flipping the shearing analogy, you may be closer to the truth of putting sheep to work. So let's watch this space. You talked about high performance computing, and this is a question that's coming via to SMS. And you sort of alluded to the notion of a digital horticulturist or a digital horticulture advisor, perhaps, utilising their desktop computer, so long as it's got parallel computing capability or functionality to do this kind of work. But from an algorithmic perspective, how soon do you see that we could be facing a situation where the algorithms, very complicated algorithms you've developed, could be made available to, if you like, ordinary non-specialist users with a view of doing their own modelling? I mean, has the modelling and the rendering of the modelling now got to the stage now that normal people, non-specialist people could do this sort of modelling themselves?
Yeah, that's exactly what we're trying to do. So we're trying to, make this not only useful to, like university or researchers, but also, ordinary people can use. I think that the pathway is to, to develop appropriate user interfaces. That's very important. Not only just the computing core, not only just algorithms that make it faster, but we need to have a friendly user interface so the ordinary users can use this software and to create different scenarios, to adjust their sprayers, for example, according to their requirements. Then that way, I think that will, that this kind of technology can really create impact. It must need to be adoptable by the, by the industry, by the community.
Yes, thank you. I mean, because that's really the challenge, isn't it? Once we meet the computational challenge, it's about getting it usable and the software usable. And, CAD went through that evolution many years ago, and some of the other more sophisticated mathematical modeling tools. So it's a great opportunity. A question from Ed up here in Armidale, not far from me. Ed, hi. When you talked about your hit and miss data and you talked about the ground truth data, how is that data being collected, the ground truth data? Is it done effectively by eyeball, by people just observing the spray droplets, or have you got some sensor-based methodology for collecting the actual hit and miss data?
Okay, I'll probably let's just share my screen to explain that. Okay. Okay, so in this case, we, for example, this is a mango orchard. We set up some, wooden slats behind the root of the trees, and we put on some water-sensitive paper onto those wooden slats. Once that is done, we use the real-world sprayer to do the pesticide application. So for those droplets that miss the tree canopies, but captured by the water-sensitive cars on those wooden slats, will make the cars, change its color from yellow to blue. And then we can collect these cars using mobile software is called SnapCard to read the coverage of each water-sensitive cars. So that's how we measure the spray result from the field experiment. And for the digital twin experiment, we also set up those, here is we set up the same, exactly the same wooden slats that matches reality in the right location with the right length, for example, height, sorry, for example, and we put on vertical sensitive cars on those wooden slats. And those droplets that touch then move to touch the water sensitive cards will do the same for us to calculate how many droplets or how many areas of a card turn from yellow to blue. And by that, we can have the digital twin experiment result. And then we normalize those results into a value between 0 and 1 and compare them. So in general, the matches, but not for every card. Yeah, I have to admit that. Yeah. I can't see you, Debbie.
No, and you've also mentioned while that slide's live that you're sharing with us, there's another question actually was querying around, whilst you've got good agreement with the modelling and the actual scenario more broadly, there are situations where there is a divergence between the experimental run and the modelling. What are the sorts of factors that come into play that explain that divergence between the measured and the model values?
Okay, yeah, so firstly, for the field experiment, the wind speed is, I think, one of the major factors, because in reality, the wind speed keeps changing from time to time, and not constant, not always the same. So that caused some variance. And also, when we read those water sensitive cards, those cards with the snap card software, so each time we read it 3 times, but it's not exactly the same for the 3 times reading. So that's why we use 3 reads to represent the real experiment result. And for the simulations, because in this case we use, because this is a long range spray process, we use the so-called random walk model that has been developed by the physicists, a while ago. We use that random walk model, but that means, it includes some stochastics of the droplet movement from nozzle to destination. So that random mechanisms could also cause some, variance. And that's why we run the simulation 3 times rather than just 1 time. Yes, the other major factor that could influence the result, this digital twin simulation result, is that the number of droplets that we simulate. I can show you an example. At the end of my presentation, I will. So here, we can simulate the number of droplets, per nozzle per millisecond. We can do, first for each nozzle, we can simulate 10 droplets coming from the nozzle per millisecond. We can also do 50, 100, 200 and 300, for example. So for the 10 droplets per nozzle per millisecond, for example, it's the result, the 3 rounds of simulation is quite different. Yeah. So when we increase the number of droplets, it's getting better. And when we increase the number of droplets to 300, for example, per nozzle per millisecond, then we have very low variances. Well, in this case, it's standard deviation. Yeah. Yeah.
Thank you. So Liqi, the LiDAR that you're using, is it being used primarily for mapping of the physical structure of the canopy orchard, or are you bringing in other physiological traits such as color, ripeness?
Sorry, David.
So when you're using the LiDAR for mapping the physical structure of the canopy orchard, the surfaces, are you invoking other data such as color and ripeness to give you to add richness to the data sets?
For the LiDAR data, for light and spray simulations, we use different strategies. So firstly, for the spray, because at this stage we only worry about hit and miss, and also the distribution of the droplets over the surface of the canopies, we don't, in fact, worry about individual leaves of that scan tree. So in that case, we can simply capture the general shape of the tree canopy. So by that we can have do a hit and miss. We can do coverage. We can also use that to calculate the canopy volume to estimate spray penetration, for example. But for the light component at this stage, we focus on orchard design. The orchard design are those conceptual trees or planting system that do not exist in reality yet. So yeah, so basically the trees I show in this presentation about for the light component is not scanned by LiDAR, but saying that we can also do, I have a slide prepared here. We can also do the existing orchards, that can be scanned by a LiDAR scanner, for example. So the first image is it's a point cloud scanned by a LiDAR, high performance LiDAR with flows. And the second and third are those simulations that were recreated with polygon meshes. So once we convert the point cloud into the polygon mesh, we can use that to capture, to intercept the light rays and estimate the light capture. Yeah.
There's an interesting question here that follows on from that around pruning. To help, for example, in-field operations, could the model be used to give or highlight recommended areas to focus on pruning with a view of increasing light interception in an operational sense?
Yeah, yes, I think so. Because we once we have that, tree structure, because we simulate the light, not only the whole tree's light interception, but also light traveling across the canopy with the transmittance, reflectance, energy capture, for example, we can exactly find out where are those branches, for example, that with very low level, with many low energy leaves. And those branches probably, be the potential target for pruning or focus of the pruning.
In the earlier question that was posed around, the divergence between our model and the actual in your orchard trials, and you talked about, for example, the effect of wind. Can that be then inverted, flipped, if you like, to allow you to study the effects of wind drift, or wind effects with a view of recommendations per orchard, per section of orchard recommendations around when to spray and how to spray, noting the wind? Can you bring the wind into play?
Yes, for example, if you have the weather forecasting data about the wind direction, about the wind speed, for example, we can do those simulations before we do the real spraying practices. According to that orchard, according to that weather, according to that specific location, for example. And with that we can find out, okay, if the wind coming from this way, if the spray go that way, what's the optimal speed? What's the optimal adjustment of those sprayer, the pressure or the nozzle types and direction, the nozzle direction, and so on, to try to find out the best solution for that specific scenario. Yeah.
Thank you. A question from Alistair here, from Downwater, I think you're now, Alistair, at the moment. So does the orchard need to be scanned to update the digital twin simulation prior to each and every spraying event to ensure application optimised? Or can you take data, say, once and then maybe, in the model environment, look at how the orchard develops over time? Does it really need to be scanned every time?
So there can be different options. So the most ideal option would be scan orchard, so that we can make precise simulations and suggestions for that specific orchard. Alternatively, if the growers don't want to scan the orchard because that could take some time, well, they can choose, for example, a similar orchard digital twin, a digital twin that is similar to their orchard, for example, the trailer system or the tree spacing and so on. So they can use those, other people's or those existing orchard digital twins to do the evaluations. But doing that means, it could be lower precision than just scanning their own orchard. And we don't have to scan orchard, doing before every spray. We probably just need to scan orchard, 4 times a year, for example. to use that, four digital twins across the year as the base to do the simulation and estimation. Yeah.
And Liqi, do you have a sense of the future of this modelling approach to ingesting of live data? For example, IoT devices. So you might have, wind, temperature, humidity data coming in live, and the model's almost automatically initialized to run. Have you got a sense of, or do you even have your own intent around ingesting live data to bring these models to live in an almost autonomous way?
Yeah, well, and definitely in future. At this stage, we haven't done that yet. But in future, I think that's definitely the direction. And definitely, the direction of the digital twin, because that means we can do parallel digital twin, real world twin, these two worlds, in parallel. So you have and with sufficient computing power, you have the input, you get quick computation, simulation, optimization, and give feedback back to the real world. I think that's definitely the future. I think it will come true anyway. Yeah.
And we have a question from Anne around, are you garnering or collecting any social or qualitative data to understand if your producers that you're working with or growers more broadly are favourably inclined towards or have the capacity to make the changes that the modelling is throwing up? I mean, are you working at the social side of this as well as a computational side?
Well, so far we have some, industry grower partners, mostly in Queensland, from macadamia industry, mango industry, lychee industry, for example. These grower partners are interested in this technology. They would like to see it becoming a tool, a practical tool they can use in future. But of course, I have to admit that, at this stage, we haven't developed that kind of user interfaces. So when developing that part, I think we still need to work with the growers, with a wide range of growers, to have their feedback, to understand their specific requirement, so that, the tool can really, appeal to their need and to be used by them. Yeah.
How long does it take when you march into a physical environment for the first time and you want to create a digital twin? How long does it typically take to create that digital twin in terms of the survey work and the assemblage in the computation environment?
So I mean, how long would it take to build those digital twins? Well, it's not long. For example, let's take the spray component, for example. I have just finished a project that was funded by DEF. It started a year ago. So within 1 year's time, a year ago we had nothing, but within 1 year's time we have built up this technology. And after that, it will be much faster to create the digital twins. For example, for the sprayer digital twin, we can easily, for example, because we have the computing core already, we can easily, for example, set up the nozzles at different locations, and we can configure the nozzles performance, the fans performance, for example, and to create a digital twin, quickly. And for the ultra digital twin, it's even faster because we only need point cloud. One way is to use terrestrial lidar. In this case, we use, for example, the Rigo lidar that scan the orchard with laser pulses. Alternatively, we can use a drone, just fly over the orchard, to use photogrammetry using cameras to capture the general shape of those tree canopies. That's much faster. Within I think a morning, half a day, we can finish the scan of a big area of the orchard. Yeah.
Good to know. That's no doubt going to get a lot of interest, that response. Digital photogrammetry for sure.
Yeah.
So question, you've talked about orchards and vineyards, Liqi. Are you doing any work in forestry, or are you aware of people working in the forestry sector with this sort of capability?
I haven't started. I haven't have official interaction with the forestry sector, but I think because they're all trees, orchard, the tree crops are trees, the trees for forestry are also trees. I think they have some elements that can be shared across these different sectors. And also for vineyard as well, using trellis system, for example, which is kind of similar with those trellis training mango trees. Yeah.
Brilliant. Liqi, look, thank you for your time. Thank you for your presentation. The questions have been coming in hot, to be honest, and that's probably one of our most energetic set of questions so far. Thank you, everyone, for being a part of the seminar. Now, feel free to reach out to Liqi directly if you want to follow up on anything you've heard, but we didn't manage to cover during our Q&A session. And don't forget, we will be releasing a recorded version of the seminar in coming days. Now, keep your eye open for our next seminar, middle of next month. Details will follow. We'll be hearing from Emeritus Professor Jim Pratney from Charlotte University. Jim's, I'm sure you've heard of Jim before. He's famous, not only as an educator, but as a researcher, but of course for his more contemporary work now on looking at employment and education trends in agriculture. And Jim and the team recently published a paper in the winter edition of the Australian Farm Policy Journal. It makes a pretty eye-opening reading, really, and points the way for some really exciting opportunities for us in the education, outreach and research game as well. So we look forward to seeing you in October. Keep your eye open for details. And thanks for joining us. And thanks again, Liqi.
Thank you. Thank you, everyone. Thank you, David.